The area of machine learning explanation has gained a lot of attention since LIME. Also popular methods proposed later are TCAF for explaining individual predictions and ACE for explaining global model behavior. They all highlight image patches that are relevant for model decisions. As you may have seen, it often can be hard for humans to know exactly what those patches are. For example, look at those image patches that are supposedly should represent a concept learned by the model. It's not clear if they show the wheels, the pavement, the combination, or simply that the gray color. So a big problem of those methods is that it requires efforts to make sense of the output of the explanation method. A problem of intelligibility. Besides, these methods do not uncover the entire diversity of mechanisms a model has learned. We notice that not all the concepts a model uses are actually captured by those explainability methods. This I will show more in an experimental work that we did later in the slides. So what do we really need to have intelligible explanations? For this question, we searched in the literature outside computer science for insights about intelligibility and identified two theories. Representational theory of mind explains how the human minds represent and reason about their environment. Also, works on human visual processing systems studies how people process visually their environment. Important things we learned are that, first, humans understand the environment through concepts that correspond to entities which come with entity types and attributes. For example, when we are thinking about an ambulance, we typically think about the flashlight, the cross logo, etc. And additionally, we might also think about attributes. For example, the flashlight is typically orange or white, and the stripes are typically yellow or blue. Note that when we describe those attributes, we use the word typically, which is in fact an important concept by itself, denoting the strength of association between entity types and attributes. For example, the stripes on the ambulance is likely to be blue more than red. Another thing we learned is that concepts might be composed themselves of other entities. For example, the chassis has wheels, and wheels have spokes, which can be further broken down to shapes, color, and etc. In fact, human brains process visual information from low-level concepts such as color, contrast, to mid-level ones such as shapes, texture, and to more abstract semantic representations of an object. Combinations of concepts can be represented through logical operators like AND, OR, which we have in fact already talked about. For example, flashlights are orange or white. Note that the combinations of concepts is important for humans to understand a complex object. To explain model behavior with entities and combinations, we developed a tool to support two different types of user needs: model behavior exploration and validation. In particular, our interpretations allow to answer multi-concept queries, such as does the model rely on the cross sign and flashlight or the blue sky for the classification of ambulances? And here are some example output. Our method shows that the model looks at both the cross sign and flashlight in recognizing a vehicle as an ambulance, which is nice, but it also shows that the model looks at also the blue sky, making the prediction less reliable. When the user does not have specific queries in mind, the exploration results from our tool, as you can see on the right hand of the slide, can support users explore around the space of model behavior explanations. So how did we build this tool? The essential idea is very simple. Since the challenge of explanations generated by different explanation methods are not intelligible enough, basically the explanations are not given in human understandable concepts. Let's directly involve humans to help the explanations to speak human language. So essentially, our method asks humans to annotate the highlighted image patches with entity types and attributes and aggregate the results to answer user queries. Our explanations are generated as follows. Given a model and a dataset, we first apply some local interpretability methods, and then post in crowdsourcing platforms the annotation task. For each image, we get a set of entities and attributes that are aggregated in the same table. In the end, we apply some statistical analysis tools to answer user queries. Here we show some results comparing our methods with others. We used a pre-trained model on ImageNet and retrieved global explanations for 3 classes. And these seem to correspond to the animals, which is expected. And in comparison, ACE returns much less explanations, mostly about the color. Then we injected synthetic biases into the dataset by fine-tuning only on those classes. Since they have spurious background biases, the model mechanisms should rely on such background information. And that is what we see in our explanations. In comparison, ACE reflects much less of this background bias. We therefore can see that involving humans to explain model decisions allows not only the explanations to be more intelligible, but also more informative while keeping a good level of faithfulness.